So it's nice because this involves applications of many things that we have done till now. It involves applications of oscillations, applications of oscillations kind of phenomena, nuclear physics, spin precession analogy, and it also involves detectors. We talk about many detectors and how they can look at these detectors, how they can change. So today I will basically give you some preliminary, and let's see how far we reach today, and then we talk about it. So this is the plan. So I'll first tell you something about how supernova explode and how they emit neutrinos. Ask questions at any point of time because I may tend to go fast over this. Okay? So yeah, so you need to zoom in. Then I will talk about neutrino flavor convergence because again neutrinos are going to start from the core of the supernova where density is very high. And you know that when you pass through different densities, then mixing angles will change, delta and square will change, and in fact, a phenomenon will occur which we never talked about before, which is there will be potential for neutrinos due to other neutrinos, not due to neutrinos, which was this period. And then we talk about how to detect supernova neutrino or not, and what we can learn. So that is the plan. So let's first talk about how explosion occurs. So supernova is generally a star which is about 10 solar masses. So it has 10 solar masses, so mass of 10 solar masses, and it has a onion ring-like structure. So outer layer consists of hydrogen, then there is helium, then you get oxygen, silicon, magnesium, and finally you go to iron. Okay? And as all of us know, beyond iron, you can't produce heavy elements because highest binding energy per nucleon. Okay? So if you need to go beyond iron, you need very, very extreme circumstances. Okay? And the only place where such circumstances can happen are very early universe, where there were no atoms, and inside supernova. Okay? So all the elements that are heavier than iron have been produced during supernova explosions. So there is, we don't know any other place in the universe where you can produce gold uranium. Okay, so what is the state? So the state is that you have this structure, in the innermost core is iron. Okay? At some point of time, everything that could be converted to iron has become iron. So you have this core inside which no nuclear reactions happen. So now, usually what happens? Usually your nuclear reactions happening which create a pressure outwards. Like your exothermic reaction will push things outwards. Gravity will push things inwards. And there is a balance. Okay? So stars usually survive because there is a balance. All stars, not just supernova. Okay? Gravity wanting to pull things inside, exothermic reactions trying to push things outside. Now once you stop nuclear reactions, there is nothing to push you outside. So of course there is this degenerate electron gas special. At some point even that fails. Chandrasekhar showed us long back that this degenerate electron gas special will start failing once this iron core reaches a mass of about 1.5 times solar masses. That's what Chandrasekhar did. So now that there is no reaction, the mass of iron core keeps on increasing as more and more iron gets produced. Density is of the order of 10 power minus 9 is here. Inside it's of the order of 10 to the power 10, 10 to the power 12 grams per cc. And at some point of time, the degenerate electron pressure can no longer support gravity, and therefore there is what's called as core collapse. So that's the reason for supernova explosion. First thing that happens is not explosion. First thing that happens is collapse. Okay, the core actually collapses, the star becomes smaller and smaller. And because this is the region where gravity is pushing it down. So this is what is happening before the core collapse. So let's first see what's happening before that, and then we'll see what happens after.
Let this inner core mass increase, which is changing.
nuclear reactions are happening. Right? I mean, you have got this oxygen and silicon outside, for example. They will keep on merging, and then you get iron. Okay, so iron content will keep on increasing. So therefore, the mass increases. So while all this is happening, what do neutrinos do? Because that's our main. So we saw that, for example, solar neutrinos, 10 eV neutrinos, we calculated, right? So if you want to stop them, you need lead of thickness of some 90, 0.1 90, something like this. But lead density is 10 grams per cc, okay, of that order. Now, if you talk about supernova core, the density is 10 to the power 10 grams per cc. Okay, so therefore, the density has gone up. Therefore, the distance needed to stop neutrino has come down. So, in fact, if you pass a neutrino, pass a density of 10 to the power 10 grams per cc, then neutrinos are almost trapped. They are just like photons. So, they will not be able to move even a few centimeters. Which means they get trapped and therefore get reabsorbed and so on. They don't come out. These are called as trapped neutrinos. Now, what do you mean they are trapped? They are trapped means they undergo different reactions. When we say neutrinos free stream out, it means they don't interact and come out. They get trapped means that they interact with other things. Okay, so these are the interactions. So, if I have an electron neutrino, it interact with neutrons, give me protons and electrons. Nu bar will give me neutrons, positron, and so on. So at very large densities, there are a lot of neutrons, lot of protons. So nu and nu bar will get trapped. As density goes down, at some point of time, when density is low enough, then a neutrino can free stream, okay, which means almost no interactions, comes out. This sort of region is called a neutrinosphere. So it means that inside the imaginary sphere, if a neutrino is produced inside the sphere, it won't come out. It will be trapped. If it's outside, it will come out. Okay, that's an approximation to zero order. We have correction, but this is enough for us. So nu and nu bar, therefore, they are these so-called neutrinospheres which work. Inside that, if they are produced, they come out. Outside, it's difficult for them to come out. These are the main reactions. Charge current reactions. If you go to other neutrinos, so let's say nu mu or nu tau, it's a different story. Because nu mu and nu tau cannot undergo these reactions. These are nu mu and nu tau of 10 MeV. Okay. So you can't produce muons, you can't produce tau. So no charge current, just like solar neutrinos. So which means the only interactions they can have are nuclear current interactions. So they can do something like this. So for example, a nu bar can produce E plus E minus, or a nu bar can produce nu bar, or a nu bar can hit other nucleons and get something else. This is called nucleon brainstorming. So two nucleons can hit against each other and make nu bar. At some point, they can interact. Individual nu can interact with nucleus and have some neutrino nucleus scattering, or it can have neutrino electron scattering also. So propagation of nu x, or this nu mu and nu tau, is much more difficult than nu and nu bar. That's because nu and nu bar only one interaction dominates. Here they don't. So in general, it's easier to calculate the outcoming nu and nu bar spectrum. It's very difficult to calculate nu and nu bar spectrum. Okay? So in fact, we don't have any reliable notations on outcoming nu and nu bar spectrum. But we know nu and nu bar spectrum is very good.
Outcoming means not from the core. From the core, from at the core it is calculated.
Yeah, from the supernova, whatever comes out completely. The point is people can't even calculate what comes out at this stage. Okay, so then I tell you that there are more complications when we think about what comes out. These are what are called as primary spectra, okay, which means no mixing, no oscillation, nothing. Just produce spectra. This is like a scattering neutrino. So the neutrino which comes out here gets scattered because of these reactions. And there are some reactions, so beyond, so Here, for example, is called number sphere. So within this area, the number of neutrinos can change. Okay, because if mu bar goes to E, means the two neutrinos have become 0. So outside that, number does not change. Then there is an energy sphere, means that outside this, energy does not change. And so on. One thing that we know for sure is this: if neutrinos actually come out, average energy of mu E should be less than that of mu E bar, should be less than that of mu x. Mu x stands for mu tau, everything. Why does this happen? See, mu E interacts with neutrons. Inside a star, when they are heavy elements, there are more neutrons. So cross section of mu E is much higher than cross section of mu E bar, total cross section. And of course, cross section of mu E bar is much larger than that of mu x, because mu x has no charge current interaction. So if you have more cross section, you will get trapped more, which means that you can come out only when you are in outer layers. Outer layers means lower energy, low temperature. So this is the sequence which tells you that whatever details of these things are, this is for sure that average energy of mu E should be less than that of mu E bar, should be less than that of mu x.
Even for what is produced inside, higher the neutrino energy, higher the cross section. So even for what is produced inside, the lower energy ones.
That's also
clear.
true.
And why there is no difference between mu x and mu x bar here?
Yeah, because cross section of mu and mu bar are the same.
The UVs are also undergoing the neutral current.
Yes, yeah. But these cross sections are much larger, much larger than these. So these dominate over these. So when I say undergoes this interaction plus all these interactions. Okay, but these dominate anyway. So forget about all this. So that's what is happening inside the star before the core collapse happens.
That process can produce heavier. That
Which one?
UV bar plus it is giving us more neutrons and more protons.
We can't produce heavy elements. Because to produce heavy elements, you need to overcome the binding energy. So you can't produce heavy element than iron.
They are free neutrons.
They are free neutrons. So for example, ideally you also have UV bar acting on other nuclei. Nuclei of hydrogen, helium, oxygen, carbon. So this is before the collapse. So now we'll see what happens after the collapse. So first thing that happens is the iron core collapses, which means that its size decreases. Okay, all the particles start going towards the center. Okay, and this continues almost like free fall, because there's nothing to push them outwards. Except that you can't increase the density of iron infinitely now. Okay, once you reach nuclear densities, then there is a hardcore potential. Nucleons can't come much closer than that. So now what happens is you have got these iron particles which are collapsing. When the density becomes much larger, then they have to bounce back. Hardcore potential will pull them out. This is what's called as a shock. So suddenly, when the density becomes more than nuclear density, then there is a shock wave produced which comes. Okay. So, and normally speaking, blindly speaking, this shock wave will blow up the star. So this shock wave comes out. What does shock wave mean? It will try to push all the material just trying to fall inside. Okay. Finally, when the shock wave comes all the way to the surface of star also gets blown. So naively speaking, this is what happens. Okay. But I'll tell you, that's not exactly what happens. This is the shock wave which is the root cause of this explosion. Okay. So again, supernova doesn't explode by exploding, it explodes by imploding. First the core collapse and then the shock. So let's see what happens to neutrinos during this time. So think of neutrinos which are around the neutrino sphere, electron neutrinos. So what does this mean? There's a sphere, just inside that there's some electron neutrinos, and they can't go out because the cross section is very large. Now the shock wave comes out. what does shock wave do? Shock wave will break up the nuclei. So heavier nuclei become lighter nuclei. Okay. Now, remember, if the cross section, if the interaction with the nuclei are coherent, cross section goes as a squared. Right? If a is the mass number, interaction is coherent, means cross section goes as a squared. If this a nucleus gets broken into a by 2 and a by 2, okay, I have got a nucleus with a by 2, another with a by 2. So now cross section goes as a square by 4 plus a square by 4. So a square by 2. So when a big nucleus breaks into 2, my cross section of electron neutrinos to interact with them becomes half. So what does that mean? Cross section becomes half, then UVs can actually move out. So when the shock wave passes a neutrino sphere, the cross section becomes half, and therefore electrons can move. In fact, you also have interactions in which if you have protons can capture UV and can give you. So let me. Okay, so two things happen. So first thing is, if nucleus A goes to a by 2, so sigma decreases. Okay. And secondly, especially with protons, so proton, electron gives you neutron and UV. So when you get protons, then this reaction happens more in forward direction. Electron capturing proton becomes faster. Okay, whereas this does not happen for heavier nuclei. Okay. So for both these interactions, basically result in higher UV energy. And this is what is called as neutronization process. It's called neutronization burst because you are producing neutrons. So what happens is, when your shock wave passes through the neutrino sphere, you will get a burst of UV coming out. And this burst lasts only for about 10 seconds. Sorry, 10 milliseconds. So this is the special burst that lasts for 10 milliseconds and has only UVs, nothing else. Now the shock wave keeps on traveling outwards, and now that the medium has become slightly rare, all the electrons can slowly start going. Sorry, all the neutrinos can slowly start going. So everything goes up. Nu E, nu E bar, nu mu, nu mu bar, nu tau bar. Everything starts going up. You also produce lots of electrons, positrons, and so on, but they can't go up because they are trapped still. They have larger cross sections. All these can go up. And in fact, in about 10 seconds, almost all the energy of collapse was gravitational collapse, right? So this mass has come down. So this energy of gravitation has got converted into neutrinos, and that energy has gone. So this energy was almost of the order of one solar mass. So take one sun, convert one sun to energy by E is equal to mc square. Whatever happens comes out of supernova within 10 seconds. It's like evaporating a sun within 10 seconds. And in neutrinos.
99% in neutrinos.
Yeah.
1%.
For shock wave, it is the neutrinos which are coming out. Shock wave means it is the neutrinos which are coming out.
Shock wave is a wave.
It is a wave.
Not particles coming out.
Particles.
Neutrinos can't move much. You see, the density is so large. Mean free path is, I don't know, 10 power minus 10 meters.
It is transferring the momentum on.
Yeah.
It's a wave.
It's a wave, right? Wave doesn't mean particles move.
Speed and what speed
Greater than speed of sound
All
and
the
density.
electrons.
Yeah. So, greater than speed of sound in that medium, but it's like 10 power 5, 10 power 6 meters.
So the neutrinos can rotate.
the speed of light. They come out much before. In fact, this shock wave starts coming out at the rate of 10^6 meter per second. After some time, slows down because see the core has collapsed. Okay? Therefore, the other star also started collapsing. The shock wave that wants to come out has to face all these infalling matter. So all the infalling matter actually slow the shock wave down because you lose energy. And actually, it turns out that when people did simulations, they found that very often the shock wave loses all the energy while overcoming this infalling matter. Therefore, supernova doesn't exist.
Is this the shock of phonons? I mean, the wave of what? Phonons. I mean, wave of what?
Call it whatever you want. A wave is transfer of energy.
Okay. It's maybe a phonon wave or say infalling matter. That means it is not connected by matter. Right? So there is infalling matter, so it is not connected by matter. So how does the wave get propagated? Some medium, some phonon.
If I hit this here, okay, if I put my pen is quite too precious. It's all here. No, and if I hit it here, the shock moves, right? So how did the wave travel here? It's exactly the same thing. So imagine it whichever way you want. So it's independent. Some matter is of course moving out, okay? But the wave is not what I mean the matter is moving out. Wave is transfer of energy. So till a few years ago, it was unclear whether our understanding of explosion is clear or not, whether supernova will explode or not. See, when I said that this shock wave will explode the supernova, that's what is called as prompt explosion. Supernova explodes. Now we know that what happens is not a prompt explosion, but what's called as a delayed explosion. So this shock wave actually loses energy to all the incoming particles and almost stalls. Okay, shock wave stalls. However, now what's happening is, of course, some of the neutrinos come out, but some of them don't, because still at 10 power 10 grams per cc, there are neutrinos which get trapped. These neutrinos, when they interact with this back of the shock wave, they will get scattered and pass on some of the energy to the shock wave. This is called as neutrino heating. So you have a shock wave which got stalled, and neutrinos, by interacting with it, pushed it. So they revive the shock wave. And the revived shock wave now travels further. I guess I have a cartoon. So this is a shock wave, it is stalled, and neutrino is trying to escape, but cannot escape, will push the shock wave. And then you produce some extra hydrodynamical instabilities, and that causes the star to go. So you need two things. You need this neutrino heating, which is neutrinos pushing the shock wave from behind, and you need some large scale convection. So this is a detail. It turns out that if you only have neutrino heating, but if you have a spherically symmetric star, then the shock wave will not be able to explode the star. This is known through simulations. However, if you allow for convections, then it is possible for the star to explode. This is trapped nebula. So supernova which was seen and recorded by the Chinese in 1054. Now we know it as the trapped nebula, and you can see it in these small telescope. Like even the API can point out that.
What is the distance of travel?
It's a galactic
And
supernova.
it is unevenly
Oh, it's galactic.
Yeah, this was visible to Dighe, right?
I mean, in 1054 it occupied the whole sky. So
Yeah,
the Chinese recording actually have pictures of this supernova. And
So a lot of neutron sources will be there. It could be collected at that time.
yeah, unfortunately
We didn't have
it's coming something like that. So this was the experiment. Yeah.
I was guessing neutrinos will come after something because the velocity of light then after.
It should not come.
And energy, what is energy of neutrinos? 10 eV. mass of neutrinos, speed of neutrinos. So they come with speed of. In fact, it's a light which won't come. I will talk about it. Maybe I can mention this is also nice thing. See, when will you see light from a supernova? When the supernova is, when the shock wave is traveling inside, you won't see the light coming out. Because all the photons that are there will get trapped. Only when the shock wave travels to the surface is blown open. Then you can see the supernova explode. So actually neutrinos reach about 1 day before the light reaches. So it actually is the other way around.
Actually, some dispersion of light.
Light scatters.
Dispersion won't come out. So I can give an example. So if you want to look at light from the center of the sun scattering and coming out to the surface, that takes about 1 million years. Okay, so don't even think about light dispersion and light coming out. Supernova light you will see only when the whole star is blown. Outer layers especially should be. See, light can be stopped by density of the order of 1 gram per cc. Right? Paper stop light. That's 1 gram per cc. So until the 1 gram per cc density part of the star is not blown up, you won't see it. So that's the possibility. So there is a huge class of people who work basically on exploring supernova. Some of them have had success, some of them have had limited success. The problem is computing power. So when people did the simulations in 1D, supernova did not explode. When they did them in 2 dimensions, they did not explode. When they did 2 dimensions with large convections, then they started exploding. Okay, but some of them explode, some of them don't explode. So now people expect that if you do it in 3 dimensions, they will explode.
What is the dimensions? I mean, did people really expect to do better, I guess, going from 1 dimension to 2 dimension without some other direction defined?
No. So the idea was the following. So what you do is when you go to 2 dimensions, of course you go to 2 dimensions thing, but then to save computing time, people first did not introduce a lot of convection. Okay? So they don't solve for the whole circle, so to say.
Okay, this is
But
the
they
partial dimension.
Yeah, they do it in one sliver. So let's take a pi of let's say 10 degrees, and you solve there. So you say 10 degree didn't help. Only when they went to a pi size of 180 degrees, then you start having large conventions. So there are a lot of people who do that. But see, for neutrinos, as far as we are concerned, all the neutrinos come out within 10 seconds. Okay? So whether the star explodes or not, shock wave stalls or not, neutrinos will come out once there is no collapse. So it's quite possible that there are many supernova which people will never see exploding. But neutrinos will come out. As many also, 10 or 15 neutrinos will come out. You will see the complete. That is still possible. So actually more supernova exploding neutrinos than those which exploding in light. So what happens after 10 seconds is not our business in some sense. This explosion of the star will take up the order of 1 day. We just want the first 10 seconds of it. That's enough for us. So I'll just tell you what comes out. Then about details about how they travel, we'll worry about. This is again what comes out of simulations. And we can give some nice arguments to say why this. Firstly, the spectra that come out of UV, UV bar and UV are almost like black body spectra. Okay, so that's because if you consider neutrinosphere as a black body, you won't have black body spectra. Okay, so this is almost true, not exactly true. Okay, so they're almost black body spectra. This is a detail which we won't go into. They actually are slightly narrower than the black body spectra. There's a reason for this, but let's not go into that. It actually happens because neutrinosphere is not a single sphere. See, different energy neutrinos, there are different neutrinospheres. Energy determines cross section. So that's a detail. That will give rise to this fact that the spectra are slightly pitched. Okay, which means slightly narrower than the black body spectra. This I already mentioned to you. Average energy of mu will be less than that of mu bar, less than that of mu x. typically energy of UV will be about 10 to 12 MeV, average energy. Nu E bar will be 30 to 16 and nu E nu tau will be 15 to 25. Okay, note that this error is much larger than this. I mentioned to you earlier that calculating nu E and nu E bar spectrum is easier because only one reaction dominates. Okay? And here that is. So these are the spectra looked at. Nu E bar and nu tau. In general, the energies are increasing order. In general, the luminosities are in decreasing order. But that's not always true. It's a good rule of thumb. Okay, so we'll stop here. So what we'll see tomorrow is, once we have this spectra coming out, nu E bar, nu bar, and nu tau bar. They will have to travel through matter and whatever is the phase. They have to come out. And during this propagation, they will change their flavor. Flavor convention after some oscillations, some MSW resonances, and various effects. So tomorrow, first I talk about this, and then we will have. So we'll stop at this.